Hello everyone, welcome back. Today in the fifth episode of Statistics for Machine Learning, we will talk about the importance of sampling and how it may create bias if not chosen properly. This is a very important step in machine learning. Imagine your model says it's 95% accurate, but when you test it on new data, it collapses. So why? What happened? Chances are your model learned from a biased sample, a small unrepresentative piece of the world. And just like talking to only one kind of person that gives you a limited view, training on biased data gives your model a distorted reality. So before we even talk about models, let's understand what sampling really means. In statistics, we can rarely study an entire population, so we take a sample. If it's chosen fairly, the sample can reflect the bigger picture. But if it's biased, say we only collect data from one region, one time, or one group, then everything that follows will be off. Remember, as I always say, your model can't be smarter than the data that you feed it. Now let's see this in a simple example. Imagine you're predicting coffee preferences worldwide, but your data comes only from a tech company in Italy. So your model might learn that everyone loves espresso and totally miss out on chai or latte drinkers elsewhere. And we call it sampling bias. Sampling bias is when the sample doesn't represent the population. Now we found out what the sampling bias is. Sampling bias also has cousins. So let's meet them. So sampling bias, the one that we know is who you collect. Selection bias is who ends up included. Measurement bias is how data were recorded. And data leakage is when your model accidentally picks at future information. Now let's see how this actually breaks machine learning in practice. Say you're training a model to recognize cats and dogs, and if 90% of your images are cats, your model might get 90% accuracy simply by guessing cats every time, right? That's look impressive, but it's useless. This is a form of sampling bias known as class imbalance. Because the majority of your data were cats, so the model was successful in recognizing cats, but how about dogs? So your model is a biased model because we feed it with a biased sample. In real world, data are rarely balanced, and if you ignore that, your model won't generalize. So how do we deal with it? To fight sampling bias, we can use several solutions. First one, use random or stratified sampling to include all subgroups fairly. Random sampling means you pick data points completely at random from your dataset. For example, randomly choosing 1,000 patients from a hospital database. And in stratified sampling, you divide your data into subgroups and then sample proportionally from each group. For example, if your dataset has 60% women and 40% men, you sample in the same ratio, so both groups are represented fairly. Another solution is to apply oversampling or undersampling to balance classes. Imbalanced means one class appears much more than another. So in oversampling, you duplicate or generate more sample of the minority class. For example, in medical data, if 5% of patients died and 95% survived, you can oversample the died case, which is smaller, to balance the sample, right? In undersampling, on the other hand, you reduce samples from the majority class, so both classes have similar sizes. For example, in the same example for oversampling, this time, you randomly remove some survived cases, which is in the larger group, until both classes are closer in number. The third solution is to collect more diverse data. For example, if you're building a mental health model, don't just use data from one city or one age group. Include people from different backgrounds, ages, and socioeconomic levels. And finally, you can use cross-validation to check how well your model generalizes. My advice in general to solve sampling bias is that if you're dealing with human data, test your model across subgroups. That's statistical fairness in action. So all of these solutions are for when bias is evident to us. But what about when it is not evident? Sometimes, as I said, bias hides so deep in the process that you don't see it until it's too late. For example, in 2016, an AI beauty contest made headlines. The model judged thousands of faces, but nearly all winners were of one skin tone. But why? They found out that the training data had very few diverse examples. They only used a very small range of skin tones. So that's not just a technical failure, it's a statistical one. And bias in the sample became bias in the output. So what can we do? Is there any solution for it? I would say yes. You need to detect it early. How do we detect it early? That's a great question, and here's how you do it. First, ask who's missing, who got included by design or accident. For example, if your data come from one platform, one country, or one time of year, you're already baked in bias, so you need to change it and include all of them. You should pay attention that statistical thinking starts before the algorithm, at the data collection stage. Now let's summarize everything we learned before moving on to model variance and bias in the next episode. From imbalanced dataset to hidden inclusion rules, these biases twist model performance. And remember, as I always say, garbage in, garbage out. Or worse, garbage in, confident nonsense out. That's even scarier. So in the next episode, we will explore the bias-variance trade-off, the art of simplicity and accuracy. And that was it. I hope you liked it. If you learned something new, please hit the like button and tell me in the comments where you have seen bias in real dataset. Maybe we will analyze them together.